Hello and welcome. Thus far in this class we've looked at position, where we are. Displacement, by how much our position is changing. Velocity, how much our position is changing with time. But our velocity also can change. Today we'll look at acceleration, the rate of change of velocity with time. We could be done, it's less than 30 seconds, and think, hey, we have our equation. But in this, let's explore what acceleration is. First of all, we see two graphs here. The blue one has a nice straight line. And the red one, the slope of our distance versus time graph is indeed changing. We know on a position versus time graph that the slope, change in position over change in time, yields velocity. And direction is important, so we indicate that again with a little vector hat over the V, or boldface. From this blue, constant slope, constant velocity. When we look at the red graph, however, we notice that for every increment of time, it is covering a greater position. Here we covered a little bit of x. Over here we cover a lot more x. Therefore, we're covering more x with time. The slope is increasing, therefore our velocity is increasing. Here we see ball position shown at equal time intervals. If we notice for this blue one here, every single time interval, it covers an equal amount of distance in an equal amount of time, therefore the ball is equally spaced. However, it's almost as if we want to track the position of our red ball with time. If we notice down here, the red ball at first does not cover much distance at all. Keep in mind, each of these red positions represent an equal time interval. As time goes on, the red ball covers more and more distance. Let's look at this, what it means for an object to be increasing in speed. Here we see it gradually.
And the advantage is Conley. And Dave gets his revenge.
Speed first increases, what we would call positive acceleration, then at the end the speed decreases, negative acceleration. To understand acceleration, we have to understand force. 300 to 400 years ago, we were postulating how the Earth could be moving and us not flying off. Isaac Newton formulated this as a law, which we'll cover later, that says an object at rest remains at rest, and an object in motion continues moving in a straight line at constant speed unless acted on by a net force. A force is a push or a pull. In this case, we see my daughter sitting in a wagon until her brother came along later on. She is obviously at rest, not moving, therefore, because all the forces on her are balanced. If there is balanced forces, an object stays at rest. However, if the forces, my other daughter, if the forces on her again are balanced, she stays in a constant state of motion. So if everything is balanced, you're going to either stay moving or stay at rest. Let's make some definitions in this principle. First of all, objects at rest remain at rest. Object in motion continues in motion unless there's no external net force. You can think about a net force. A force, is crudely speaking, is a push or a pull. What we're trying to say here, however, is that if there is no net force, we will have no change in velocity. However, if there is a net force, there will be a change in velocity, and a change in velocity is something we know as acceleration. In this picture here, we see my daughter, Emily, being pushed around by her older sister, Madeline. Of course, I first took a picture, and then I said, no, your little sister is not a toy. If you're a youngest child, congratulations on surviving your older siblings. But it was fun. Nobody was hurt in this, and it was funny to see. Okay. We can think about positive acceleration, which will cause there to be a change in velocity, is a push in the positive direction. That's when Madeline started moving her sister around, she pushed her forward. Negative acceleration, when I said, please, your sister's not a toy, please stop. Negative acceleration is a push or pull in the negative direction. In this case, Emily was moving forward. When Madeline pulled back on her, she stopped. Negative acceleration. Gravity is classic negative acceleration because it is always pulling things downward. Let's look at this in action. Here we have a car on a driveway. Because it is icy, there will be a net force pulling it down the driveway. When there is a net force, objects will accelerate, pick up speed, and go down the ramp. To our numerical definitions over here, we can think about displacement is the change in position. Velocity is the change in position or the displacement with time. Acceleration is the change in velocity with time. Again, when I put these little hats over here, it simply means, these little hats over here, it means that direction is important. The units of acceleration are, you can look at this, the change in velocity over time, meters per second per second. Of course, this looks a little awkward, so we will usually use meters per second squared. Let's look at an example. If a pitcher throws a 90 mile an hour fastball in baseball over a much large period of time, the catcher catches it over a very short period of time. We know that, well, it's going to be a positive change in velocity for the pitcher, negative change for the catcher, but the absolute value or the magnitude of the ball is the same for both. However, you can look at the time interval for the catcher is very small. That down arrow means small, and therefore the acceleration, which is equal to the change in velocity over the change in time, is very large for the catcher. The catcher has to wear ridiculous amounts of protective equipment. Let's consider the car here. It's slowing down from -15 going to the left to -5. In the case of the car slowing down, I wrote down our equation here. Of course, we see that acceleration is a change in velocity, and then I plugged in my numbers. We went from our initial, it's final minus initial, but our acceleration came out to positive value. One can think, how can we have positive acceleration when we have negative velocity? The bottom line of this is, although the car is moving to the left, negative velocity, the acceleration is a push to the right. Therefore, since it's pushing it, it is slowing it down, and we have acceleration as the push to the right. Let's think about how we can graph this motion in a variety of different ways. I've drawn a little diagram down here so we consider. Let's imagine at this first time, purple, we are at position 4, far away from the origin. Over time, we move towards the origin, and we notice here we have a very large slope during this time, so that implies a high negative velocity. When we come towards the middle, our slope here is essentially zero velocity. We're changing our velocity, so I'll plot the 0 over here, but our position here is way over here, far to the left. When we come over here to the right, again, short time later, we're moving to the right. We're going with time, of course, here. At this green dot, we have a very large positive slope, which implies a positive velocity. Notice how our velocity is changing with time, our slope is changing over here, and we have a nice happy parabola, and we end up over here. Essentially, if we were to think about the motion here, we were originally coming to the left, we reverse direction, and our object comes back over here, the green, to the right. When we want to think about what can we learn from each one of these, our slope here, of course, we could look over here, is the change in position over the change in time. And I'm going to write this down here on the position graph. Our slope is equal to change in position over change in time, which of course gives us our velocity. On the velocity graph, however, this is the change in velocity on the vertical axis, change in velocity, we're going up, over the change in time as we're going to the side, change in velocity over the change in time, of course, is the acceleration, and direction is important. Finally, our acceleration, we note over here that our acceleration is always positive slope in this black section of time. And then again, when we come down here during the red section of time, again, we always have a positive slope, which implies positive acceleration. It's as if the object down here was originally going, it starts out going to the left, slowing down, and then starts going to the right. It's as if there's always a large force or acceleration pushing it, acceleration pushing us to the right. Let's consider the areas. The area of each graph, of the velocity graph, is equal to the average velocity times time. If you took the area of a triangle, we'd get that is equal to the change in position. In this first case, the black section, because we have we're in the negative section, we have a negative area. In the red section, we have a positive area, positive displacement. This would tell us over the entire time our net displacement is 0. In the acceleration graph, however, our area would be acceleration times time is a change in velocity. What this implies is that we have a very large positive change in velocity, again, given by the area. We don't really learn too much over here, although we could learn a little bit more, another topic. One final example, a whole bunch of stuff to learn. Let's look at this problem over here. Cars' velocity are shown before and after. Time intervals are identical, and I'm underlining key points here. And magnitude, we want to know the magnitude of the acceleration, the absolute value of the acceleration. We remember the very definition of acceleration is change in velocity over change in time, which happens to be v final minus v initial over r time. I've written down the change in velocity for each of these objects. Keep in mind, going positive to negative, we're essentially reversing direction. So when I want to rank these, C is obviously the greatest because, again, I'm using magnitude. Time is the same, so really all I'm looking for, since time is the same, I'm really just looking for change in velocity. So C is greater than A, which equals B, which equals D. Last example. We have 3 cars and we're given velocity. It's always key to note what type of graph versus time, and we're asked to find a few different things. The first happens to concerns the displacement. We remember displacement is the area under each graph. Area. In this case, we could think about, of course, here we have a positive dx, and I'm going to use a little bar to make sure this is positive. We have 0. Because the positive and negative, we have negative over here, positive over here, they cancel. So we have 0 change in position here, and here we have a negative dx because we're all below the x-axis here. So the displacement, B, is greater than C, which is greater than A. Now let's look at distance. Distance does not matter whether you're going forward or backward, but simply how much you cover. So here we can just look over here. We have 5 blocks. Distance times time. Over here, if I looked over here, I'm going to say we have 4.5 blocks over for B, because again, we're looking at the distance. Over here, you could look at this. Yes, we have about 1 times 2.5. 1 times 2.5 times a half. You have total here, you have about 2.5 blocks. Again, figuring out the area of each of these. And so in this case, A is greater than B, it's greater than C. We're thinking about what is the definition of distance when we do this. Finally, acceleration, again, we remember is the slope. So in this case, C has a positive slope, and we're not asked for magnitude, so we just want to look at this. C has a positive slope, which is greater than A, which has a 0 slope, which is greater than B, which has a negative slope. We've ranked things. Okay, sorry about the length of this lecture, but what did we learn? Perhaps too much? Well, maybe. We'll see, and we'll have time to go unpack this. Fundamentally, acceleration is a change in velocity with time. The cause is a net force. Essentially, positive acceleration will make the velocity more positive. If you're at rest, a car rolling down the hill might be going 10 meters per second, as we saw, because that is a push in the positive direction. But positive acceleration can also mean an object is slowing down. If we went from negative 10 meters per second to negative 20 to negative 10, much like the numerical example we saw, the car was moving to the left, negative velocity, but got pushed to the right, positive acceleration, therefore it slowed down. We then looked at the idea of graphs, position, velocity, acceleration. Each one tells us a different thing. But there is a close correlation. Some are more easier than others. However, the position graph, our slope, you can just look at what is the slope. Change in position over change in time is velocity. On the velocity graph, change in velocity times time is area. However, when we go the other way on a velocity graph, average velocity times time equals position. And finally, last but not least, we combined all of these fashions into a more usable format we'll call the kinematic equations. We'll have ample time to look at those as well. Thank you very much, and take care.